The ENIAC, a behemoth of vacuum tubes and wires, filled a room. It marked the dawn of the computing age in the 1940s. From those humble beginnings, we have witnessed an astounding acceleration in computing power. Transistors replaced vacuum tubes, shrinking computers and boosting their capabilities. The integrated circuit further miniaturized components, paving the way for the microprocessors that power our modern world. Supercomputers, once confined to research labs, are now tackling challenges in fields as diverse as medicine, climate modeling, and astrophysics. They simulate the birth of stars, predict the path of hurricanes, and help us understand the very building blocks of life. To understand where we are headed, we must first examine the forces that have driven us this far. Gordon Moore, co-founder of Intel, made a prediction in 1965 that would become a self-fulfilling prophecy. Moore's law stated that the number of transistors on an integrated circuit would double approximately every 2 years. This prediction became a guiding principle for the semiconductor industry. For decades, Moore's law held true, driving innovation and fueling remarkable progress. Chip manufacturers found ingenious ways to shrink transistors and pack more computational power onto a single chip. However, as transistors approach the size of a few atoms, quantum effects begin to interfere with their operation. This slowdown of Moore's law does not signal the end of progress, but it does herald a shift in the landscape of computing. To continue pushing the boundaries, we must explore alternative paradigms. Supercomputers, the titans of the computing world, embody the pinnacle of conventional computing power. These behemoths, comprising thousands of interconnected processors, can perform quadrillions of calculations per second. Fugaku, the current leader, boasts an astonishing 442 petaflops of performance. These computational giants are tackling some of humanity's most pressing challenges. They are helping us understand the complexities of climate change, design life-saving drugs, and unlock the secrets of the universe. However, even these technological marvels have their limits. One primary challenge is heat dissipation. Packing billions of transistors into a confined space generates immense heat, requiring sophisticated and energy-intensive cooling systems. Moreover, the traditional approach to computing based on the von Neumann architecture is inherently limited by the need to move data between the processor and memory. To overcome these limitations, we must look beyond the confines of conventional computing. Quantum computing harnesses the bizarre and counterintuitive laws of quantum mechanics. Unlike classical bits, which can represent either a 0 or a 1, quantum bits or qubits can exist in a superposition of both states simultaneously. This unique property, along with the ability of qubits to become entangled, allows quantum computers to perform computations in ways that are impossible for their classical counterparts. The potential applications of quantum computing are vast and transformative. They could revolutionize fields like medicine, materials, science, and artificial intelligence. Quantum computers could be used to design new drugs, create novel materials, and develop AI systems with human-like cognitive abilities. However, building and controlling quantum computers is a daunting task. Qubits are extremely fragile and susceptible to environmental noise, making it difficult to maintain their delicate quantum states. Despite these challenges, the field of quantum computing is rapidly advancing. Companies like Google, IBM, and Microsoft are pouring resources into developing practical quantum computers. Artificial intelligence, once the realm of science fiction, is rapidly becoming a reality. From self-driving cars to virtual assistants, AI is already transforming our world in profound ways. At the heart of this AI revolution lie GPUs, or graphics processing units. Originally designed for rendering graphics in video games, GPUs have proven to be remarkably adept at handling the massive datasets and complex computations required for AI applications. Unlike CPUs, which are optimized for general-purpose computing, GPUs excel at parallel processing. They can perform the same operation on multiple data points simultaneously, making them ideally suited for tasks like image recognition, natural language processing, and machine learning. The rise of AI has fueled an insatiable demand for GPU computing power. Cloud computing providers are investing heavily in building massive data centers equipped with thousands of GPUs to meet the growing demand for AI services. This is leading to an explosion of innovation in AI applications across a wide range of industries. The relentless pursuit of computing power comes at a cost measured in watts. Data centers, the beating hearts of the digital world, consume enormous amounts of energy. If the global data center industry were a country, it would rank third in electricity consumption, behind only China and the United States. This insatiable appetite for energy has significant environmental implications. Most data centers rely on fossil fuels to generate electricity, contributing to greenhouse gas emissions and exacerbating climate change. Tech giants are investing in renewable energy sources like solar and wind power to reduce their carbon footprint. They are also designing more energy-efficient data centers using techniques like natural cooling and waste heat recovery. However, these efforts, while commendable, are not enough. As the demand for computing power continues to grow, we need to find fundamentally new ways to compute more efficiently. The quest for ever-increasing computing power is pushing us beyond the limits of conventional technologies. Researchers are exploring a range of emerging technologies that promise to revolutionize the way we compute. Neuromorphic computing, inspired by the structure and function of the human brain, aims to create chips that process information in a fundamentally different way than traditional computers. These chips, composed of artificial neurons and synapses, can learn and adapt over time, potentially leading to more efficient and powerful AI systems. Optical computing, which uses light instead of electricity to transmit and process information, offers the potential for significantly faster and more energy-efficient computing. DNA-based computing harnesses the information storage capacity of DNA molecules to create ultra-dense and energy-efficient storage systems. DNA can store vast amounts of data in an incredibly compact form, making it an ideal candidate for archival storage and other data-intensive applications. These are just a few examples of the many exciting developments on the horizon of computing. While it is impossible to predict with certainty which of these technologies will ultimately prevail, one thing is clear: the future of computing is bright, and the limits of what is possible are constantly being redefined. As we continue to push the boundaries of what's possible, we can only marvel at the wonders